SwayamPrabha. Digital India. Educated India.
Welcome to lecture number 5. So today we'll be talking about kinematics of serial arm manipulators. And kinematics deals with the study of position, velocity and acceleration without regard to forces acting on the system. So we'll start off with how do we assign axes on the various joints that make up the serial link, and then we'll see how do we do forward kinematics and inverse kinematics in subsequent classes. Okay. So today's class is about kinematics and DH parameters. Now we have we had studied in the last classes, the last couple of classes, that in a serial arm linkage we have links which are connected by joints. Joints can be revolute joints, or they can be prismatic joints, and each of these joints have 1 degree of freedom, and they have an axis about which they can translate or they can rotate. Now let's look at the case of a link and see what is the relation between the two axes. How many parameters are required to define the relation between two axes of one link? Okay, then we'll see how many parameters are required to define the axis between subsequent linkages. So first let's look at a robot link which has a 3-dimensional shape. So this is in 3D, so it can have all funny shapes. So this is a very funny shape of a 3D linkage. Okay, so this is one joint, and the other joint is this side. So this is one joint and the other joint is here. It is in 3D, so it can have all funny kinds of shapes. Okay, so they can point in any directions, but this has two linkages, two axes rather. This is one link with two axes. Now the first thing that we need to do is we need to assign an axis. Okay, so on the left side, this is a revolute joint, so we define the axis like this. This is my axis I minus 1. And on the right side, we have an axis which is defined like this. This is I. So the first thing we have done is to define an axis about which it is rotating or it is translating. Now the next parameter that we need to do, how do we find the parameters that relate these two axes? So what we see is that these two axes are not parallel. Okay, they are skewed lines. So what we do is I make another line here which is parallel to this. So this and this are parallel now. Now when they are parallel, these two lines are parallel, I can define this angle alpha I minus 1. So there's an angle between these two lines now. This angle is called the twist angle. So alpha I minus 1 is called the link twist. Okay, this is one parameter. Now I can also draw a straight line from this point. So I can draw a perpendicular line onto the other axis. So this is a perpendicular line, the shortest distance between the two axes. So it is AI minus 1. So the other parameter is called AI minus 1 and is called the link length. Okay, so when we have a single link and we have two axes, then we see that there are two parameters which define the difference between these two axes. One is the link twist. What is the twist between these two axes? And the other is the link length. What is the perpendicular distance between these two axes? Okay, this is for one link. Now on that one link, I'm going to add one more link, and then I'll add one more link and proceed like that. Okay, so what we do is I will draw another linkage system which has two links. This is also in 3D, so the shapes are always very funny. Okay, so this is a 3-dimensional link in 3D, so the shape can be a little funny at times. So this is okay, so this is another link which is connected to the front side, and this is my okay, so on this side, this is my link. Now this was the previous link, was only one link, which is this one. Now on this link I've added one more link like that. Okay, and that is what I'm drawing. So this is I, this is going to become I plus 1. Okay, so we have defined our axis as in the previous case, which is one axis is like this and the other axis is like that. Okay, and in the first case we saw that if you draw another line which is parallel to this axis, Okay, then we can define an angle alpha, and there is a distance, shortest distance, which is ai minus 1, alpha I minus 1. Okay, so 2 parameters for one link. Now let us fix our xyz axis of the xyz frames. So this axis is what we call my z frame. So I put my z axis like this. Let me put some other color and say that this is my z axis. Okay, along this is my z axis, so that is z I minus 1. Okay, now x I minus 1 is along this perpendicular distance, so this is x I minus 1. And what about y? As per right hand rule, it is that side, y I minus 1. Okay, so we have x, y and z we have fixed. Now on the other linkage, okay, we have another axis out here. Okay, so this is my z axis, is always the axis of rotational translation, so that is xi. This is xi. The shortest distance between the z's is xi, and y completes the right hand rule, so y will be going that side. Okay, so that is y. So this is the axis, I minus 1th axis for link I minus 1, and this is link I. So that is my axis xi, yi, zi. Okay, now how many parameters would define the relationship between the axis I and the axis I minus 1? We have seen that a single link already has 2 parameters, alpha and a. So alpha and a we have already seen. Okay, what are these two? Now how do we find that? So let us assume that I'm going to move the axis I minus 1 and align it with axis I. How many translations and rotations are required? That would mean that many parameters are required. So what I do is, first we rotate the z axis by an angle alpha. So my first transformation is alpha, and align this axis with this axis. Okay, I have rotated and aligned the two z axis. So alpha, what is the first thing I did? Okay, let me write down the steps so it becomes clearer. Number one is you rotate zi minus 1 and align with zi. That's the first thing we do. Then the next thing we do is we translate okay, the axis I minus 1, okay, by distance ai minus 1. So from here, when I'm translating, what we are doing is this origin is translated and it's moved here. Okay, so you can see that xi minus 1 is this side. So xi minus 1 is here, zi minus 1 has come here, and yi I'm not drawing because yi just completes the right hand rule. Okay, so what are the two transformations? One is I rotated the z, okay, and aligned it with the zi minus 1 and zi are aligned, okay, by rotating by an angle alpha here. Then I translated I minus 1 axis by ai minus 1, which means the link length, and the origin has come here now. Now you can see that the zi minus 1 and zi are aligned, but the xi and xi minus 1 are not aligned. Okay, so what I do is, next I rotate this one and I bring my I bring this one here. So this is xi minus 1, and there is an angle theta there. Okay, and then so third one is align xi minus 1 and xi, okay, by rotating by an angle theta. Then what I do is, the origins are still not same, then align origins by moving by a distance d. So now I move this origin up to here, and this is my distance d. Okay, so now so what we have seen is there are 4 transformations. One is alpha, one is a, then there is theta, and then there is d. Alpha, a, theta, and then d. So using these 4 parameters, we are able to align axis I minus 1 with axis I. So it means that the relationship between the axis of 2 frames which are aligned to link I minus 1 and link I can be defined by 4 parameters. Now let me draw it again, because this is something we need to understand very clearly. Okay, the very basis of robotics. So let me draw it again. So we have one linkage here. Okay, so this is one linkage, and this is another one there, and this is having in some other direction. Okay, so this is in some other direction. So the first thing that we do is, this is my linkage I minus 1, this is linkage I assign my z-axis, z-axis. Okay, what is the z-axis? The z-axis is the axis of rotation or translation. So this is my z-axis. Okay, that's my z, that's my axis. Okay. Now, what we do is we find the shortest distance between this. So in order to do that, what I do is I draw another line which is parallel to this one. So this becomes parallel to this. Okay, so this is an axis, so it becomes parallel to that, and this is my shortest distance. Okay, this is perpendicular. Okay, so we see that there is an angle alpha there, alpha I minus 1, and this there's a distance I minus 1 there. Okay. So what we do first is, number one is I put my z-axis along the axis of rotation or translation. In this case it's rotation, so this is my z-axis. Okay, x-axis is the shortest distance, so that's my zi minus 1. This is xi minus 1. That's the first thing I do. Y-axis completes right-hand rule, so there is no point in writing that or drawing that. Where is the next axis? The next axis is on the other frame. So on the other frame, let's say this is my z-axis. It is also along the axis of that frame. Now let's say that the xi is in this direction. Okay, it is the shortest distance to the next frame. Suppose we can imagine that there is one more frame here now. So here there is one more frame. Okay, so there is one more frame there. Okay, and this is the shortest distance to that frame now. Okay, now we want to find how many parameters are required to align xi minus 1 with xi axis. So the first thing that we do is we rotate by an alpha I. So we rotate by an angle alpha. So this is my angle alpha. Then what I do is I translate by a distance a. So when I rotate by an angle alpha, what would happen is the zi will come here. So let me change the color. Okay, so the first, when I align it, what will happen? Zi will come here. Zi minus 1 has come there. Okay, I am rotating. Now they are parallel. You can see the zi minus 1 and zi are parallel. Then I move it here. So what will happen? My zi will come here. Zi minus 1 and z are parallel now, and the origin has shifted here. Okay, and xi is in this direction. Xi minus 1, sorry. Okay, so we have two transformations, alpha and d. Next, what I do is I align the x-axis. So I rotate the x-axis like this by an angle theta, and this becomes my xi minus 1. Now the xi and the xi minus 1 are aligned. I have rotated by an angle theta. Okay, so I got my third parameter. Then we see that the origins are still not the same. So what I do is I move this up like this from here to here. Okay, by a distance d. Okay, so this distance is my which is called the link offset, which is here, which is d. So how many parameters did we need to align this I minus 1th frame with that of the ith frame? We needed 4 parameters. What are the 2 parameters? 4 parameters: alpha, which is called the link twist. Okay, then alpha a is called the link length. Theta is called the link angle, and d is called the offset. It's called the offset distance, okay, between the origins, or the distance between the origins. So we see that in 3-dimensional shape, when the shapes can be of any type in 3D, we need at most 4 parameters to align 2 axes in 3D. Okay, and these 4 parameters are called the DH parameters. So these 4 are called DH parameters, and they are also called Denavit-Hartenberg parameters. Denavit-Hartenberg notation, they are basically called. Okay, so that brings us to how do we assign axes. So let's proceed. How do we assign axes between two linkages? So the z-axis is the axis of rotation or translation. So let me draw it here. I'll do for 3D shape, then I will do for a more nice looking shape. This shape is not very nice looking, but it's in 3D, so we get the idea. Okay, so these are 2 linkages. The z-axis is the axis of rotation or translation. So this is the rule. Z-axis is the axis of rotation or translation. Okay, so let's draw it. So this is my axis of rotation or translation, this. Okay, so this becomes zi minus 1. This is zi. Now, is it unique? No, it can be pointing that side or it can be pointing this side, because an axis is in either direction it can go. Okay, so we simply say that it's the axis of rotation, and for our case we say that Zi is that side. Okay, now the second axis that we do, x is the shortest distance. So here we have seen that SHO, shortest distance between z's. Okay, so we have seen in the in the previous slide that what I do is I draw a line which is parallel to this, and this is my angle alpha. Then I find the shortest distance like this, and this is my shortest distance, and say this is my z-axis and this is my x-axis, xi minus 1, zi minus 1. Okay, so z-axis is the axis of rotation or translation, x is the shortest distance between the z's. Now in the case the z's are intersecting, then x is perpendicular to the plane containing the z's. So if z's are intersecting, then x is perpendicular to plane containing z's. Okay, now y-axis we don't write because it just completes the right hand rule. Okay, what are the other parameters? So I have assigned my axis by just following the simple rule z and x. Z is the axis of rotation translation, x is the shortest distance between the z's. Now if the z's are intersecting, then the x is perpendicular to the plane containing the z's. I'll give an example. So we have assigned our axis, so my next axis is here. Okay, so this is my next axis, zi, and my xi is that side. Okay, so we have completed our assignment of x and z. Now what are the other two parameters? We define our parameters now. So what are the parameters? A, alpha, d and theta. Okay, so let us define our parameters now. So A, alpha, d and theta. A is the link length. A is the link length. Okay, is the distance. So this is the distance from zi to zi minus 1 along xi. Okay, now so ai is the link length, which is the distance from the xi to the xi minus 1 axis along zi to zi minus 1 axis along the xi. Now what is alpha? Alpha is the link twist. So this is the angle between zi to zi plus 1 along xi. Okay, two parameters, A, alpha. What is di? This is the distance from, so this is the offset distance. This is the distance from xi minus 1 to xi along zi, and A, alpha, d and theta. So theta is the angle, let's call it I. Okay, theta I is the angle from xi minus 1 to xi along zi. So these are the four parameters, and these are the names: link length, link twist, offset, and link angle. So this is also called the link angle. Okay, now we just go back a little bit. Let us go back here and look at this for parameters. So alpha is the link twist, which is the angle. So this is my angle. Okay, so this is my alpha. Okay, which is clear is the angle between the z-axis. Okay, so this is angle between z. Okay, then what is A is the link length. What is that? That is this much. What is that? This is the distance between z's. Okay, then we have the link angle theta. What is theta? Theta is the angle between the x-axis. So this is angle between x's. Okay, and what is d? D is the distance between the two origins, that is this much. Okay, so d is the offset distance. So this is distance between x's. Okay, so what you see here is that alpha, A, theta and d is very easy to remember what is what. So alpha is the angle between the z's, A is the distance between z's, theta is the angle between x's, and d is the distance between x's. Now you see that there is no y-axis involved here. Why? Because it is fixed as per right hand rule. So these 4 parameters have to be found when we proceed with our kinematics. So the first thing we need to do is to assign axis, and then proceed. How do we assign axis? We assign axis as the z-axis is the axis of rotation or translation. X-axis is the shortest distance between the z's, and in case z's are perpendicular intersecting, then it is perpendicular to the plane containing the z's. Okay, let's take an example. We start off with very simple examples. Let's take a very simple example. So we have a manipulator system like this. So we have 3 links like this. Okay, this is my manipulator. There's a link here and there's another link there. Okay, so there are 3 revolute joints. This is 3 degree of freedom. Okay, it has 3 revolute joints. The first thing we need to do is to put our z-axis. Okay, number 1 rule, z-axis is axis of rotation in this case. Okay, now because it is rotating on the plane, if you can imagine, the z-axis is pointing out, so this is z0. Okay, and we put the 0 as the base frame, so 0, x0, y0, z0 is the base frame or the reference frame which does not move. Okay, now we have defined our z-axis. Z0 and z1 is the axis fitted onto the first link, z2 is the axis fitted onto the second link, and z3 is the axis fitted onto the third link. Okay, so 0 is our reference frame. First link we put axis 1, second link we put axis 2, and third link we put axis 3. Now the second thing we need to put is x is the shortest distance between z's. Now the first one, the x0, we normally put it horizontal, but it can be anywhere actually because it's a reference frame, it's not moving. Okay, so the first one I'm putting it like this, x1, sorry, x0. The second one, x1, is the shortest distance between z0, is the shortest distance between the z's. Okay, so the first fellow I'm putting it there, the second fellow is here, so this is my x1. Okay, so this is the x is the shortest distance between the z's, so z1 and z2, that is the shortest distance. Now x3 is here, that's sorry, x2 and x3 is here. Okay, so what we have seen is we have put our z-axis, then I've put my x-axis. The x0 can be in any direction. Normally we put it horizontal. Okay, but it can be in any direction actually, because the angle is the relative angle between x0 and x1. Okay, so it's a relative angle. So this is my theta 1, this is my theta 2, and that's my theta 3. Okay, so this is my, put my z-axis, x-axis. Now let's make what we call the DH parameter table. So DH table. So the DH table contains all these parameters, a, alpha, d, and theta. Okay, so this is my DH parameter table, right? And this is my axis 1, 2, and 3. Now, in order to remember what we have seen here is that a is the distance between z's, alpha is the angle between z's, d is the distance between x's, and theta is the angle between x's. So these two are to do with z's, these two have to do with x's. Okay, there is no y in there. So one is an angle, the other one is a distance. So if you just to remember, if you just write this is distance between z's. Okay, this is angle between z's, this is distance between x's, and this is angle between x's. Okay, just to remember which one is what. Then we say this is the 1, 2, 3, 4 other joints, which basically mean this is the joint 0 and 1. This is between joint 1 and joint axis 1 and axis 2, and this is between axis 2 and axis 3. This is the meaning. Okay, although we write 1, 2, 3, it basically means what are the a, alpha, d, theta parameters between the previous link and that link. So in this, the first case, it is 0 and 1. So look very carefully at the 0 frame and the first frame. The origins are the same. Okay, so the origins are same, means the distance between z is 0. So the z-axis z0 and z1 are here. Okay, so z0 and z1 are the same line, so basically there's no distance between them, so it is 0. What about the angle between the z's? Again, is the same line. Okay, so it is 0. There's no angle between them. Now what about the distance between d's? What is the distance between x's? Now x0 is here and x1 is there, and they're intersecting at the origin, so again there is no distance, right? Now what is the angle between the x's? So the angle between the x's is theta 1. That is my angle, theta 1. Now when this manipulator rotates, what will change? A, alpha, d cannot change. Theta will change. So out of those 4 parameters, normally only one parameter will change. So for a revolute joint system, the angle theta will change, and for a translating joint, the distance d will change. Okay. Now the next one, where is axis 2? Axis 2 is origin is here. Okay, look at z2, look at x2. Okay. Now what is the distance between the z's? So distance between z means the z's of axis 1 and axis 2. So this is my link length, let's call it L1. So this is my link length L1. Okay. Then alpha is the angle between the z's. The z's are parallel, so there is no angle between them. What is the distance between the x's? The x's you can see are intersecting. So x1 and x2 are intersecting at that point. So it is intersecting here, right? So again the distance is 0. And what is the angle between the x's? So x1 is in this direction if I extend it. So this is my x1. Okay. So if I extend x1, it comes here. So the angle between x1 and x2 is theta 2. So my variable is theta 2. What about the third one? So third one means the parameters between the second axis and the third axis. Again, note the direction of the z2 and z3. They are parallel. Okay, they are coming out of the board. So what is the distance between them? Let's say the distance between them is L2. So this is my link length L2. Okay, and what is the angle between them? They are parallel. So there is no angle between them. Both these axes are parallel axes. So it is 0. What is the distance between the x-axis? Now you can see that x2 is in this direction. So if I draw it in a red color to understand better, so this is my x2 and this is my x3. So they're intersecting at that point, right? Similarly, the x1 was like this and x2 was this side. So they're intersecting. So there is no distance here, okay, because the x's are intersecting. And what is the angle between the x's? So the angle between the x's is that angle. Okay, so this is my x2. What is the angle? It is theta 3. Okay, so what we have seen is that this is the DH parameter table, which gives us the angle, which gives us the values of the 4 parameters, A, alpha, D, and theta. And out of this, in a revolute joint system, when the robot moves, what will vary? And these 3 will vary, theta 1, theta 2, and theta 3. The others are all constant. Okay. Now this basically gives us the relationship between one frame to the previous frame. Okay, that is what this is giving us. Okay, so if you want to go from one frame to another frame, how many transformations are required is shown by this table. Now this is one example, and let us move on to the next example of a case where the z-axis are intersecting. Okay, in this case they were all parallel, so it didn't matter. Now let's look at this example here. This is a robot. Okay, and this is a link here. Okay, and this is the structure of the robot. So the first thing when you see a robot, robotic manipulator, we have to understand which are the joints, which are the degrees of freedom, and when it moves, what changes. Okay, first of all, whether it's prismatic, whether it's revolute, and if it is prismatic or revolute, where is the axis? Okay, so how does this one work? If you can imagine, first axis is this one, which can rotate about that. So if you can imagine this full body, okay, can rotate about this axis. That's a vertical axis, which is the revolute axis. The second axis is this link here can go in and out. Okay, so this is a translating joint. So this is a revolute joint, this is a prismatic joint. And the third one can rotate about that axis, which is at the wrist. So this is revolute again. So it's revolute, prismatic, revolute. Please try to understand very carefully how, when this moves, how does it move? Okay, so the first is this body can rotate. Okay, so if I see it from the top view, if I draw my top view like this, okay, this is my top view. Okay, now this is the axis which is coming out, the first axis, okay, which is coming outward. So it can rotate like that. So it can go here or it can go here. Okay, so it is rotating axis. The second axis is a prismatic axis which can move front and back by the distance d. Let's call it d. The third axis is at the wrist, so it can rotate about this axis, okay, either clockwise or anti-clockwise. So this is called my, this is a revolute joint. So this has total of 3 degrees of freedom. Okay, now let's assign our frames. So let's try and assign our frames onto this robot. I'll just draw it again. So the first frame is going to be my z-axis. So where is my z-axis? The z-axis is like this. Let's say it is like that. Now very often we have to understand this carefully so as to simplify the number of transformations that are required. Okay, so the first axis I'm putting it here. I could have put it here, but if I put it here, what will happen? This additional transformation of the distance will come. Just to reduce it, what I have done is I have put it up there. Okay. So my first axis is my Z0, the reference frame, and the first axis is the first frame. So Z0 and Z1 is the same axis. Okay. Now we put Z2. Where is Z2? Z2 is rotating. Sorry, it's a translating axis, so it can move in this direction. So that's my Z2. Okay, that's my Z2 axis. It's a translating axis. So if you just go back and see, so this can translate front and back. Okay, if you can imagine, this is one link, this is second link, there's third link. So the second link is something like a hollow cylinder. Okay, this is my second link, and the third link is a long linkage like this, which is inserted inside here. So this is inserted in there, and this can move like that. Okay, that's a prismatic joint. Now, okay, so Z2 is here. What about Z3? Z3 is that the rotation axis there. Okay, so I have Z0, Z1, Z2, Z3. Now you see something that Z1 and Z2 are intersecting. Okay, so they are intersecting at this point, which is here. So when I'm going to assign my x-axis now, the x-axis will be perpendicular, okay, to the plane containing the z's. What is the plane containing the z's? This is the plane containing the z's. Okay, that's my z plane. So this x-axis is going to be perpendicular to that. So I say my x-axis is here. Okay, so this is my x-axis, which is x0, x1, and x2. I put them together. Okay, where is my x3? My x3 is there. Is that okay? So let's say there is some length there, which is so my variables. What are my variables? I need to see those now. So there is a θ1, which is here. There is a d2, which is there, and there is a θ3, which is there. Okay. And maybe if this is going by that much distance, so the distance between the origin from here to there, let's say, is a length L. Okay, or let's call it an offset distance, some distance of maybe L. Okay, so basically the d2 moves from here to here. That is my variable d2. But from this origin of 0 to the origin of there is also a fixed length, which is d there. Okay, so we can neglect that also at the moment. That's okay. The same thing. Okay, so now let me write the dh parameter table. So it is a, alpha, d, and theta. Okay, just for understanding, we have 1, 2, and 3 axes. So this is 0 to 1, 2 to 1 to 2, 1 to 2, and 2 to 3. So this is the distance between the z's. This is the angle between z's. This is distance between x's. To remember, this is angle between x's. Okay. Now the first frame, 0 to 1, 0 to first frame is given by the distance between the z-axis. Now look at z0 and z1, they are the same axis, right? So there is no distance between them. What is the angle between the z's? Again, there is no angle. Okay, they are the same axis. Now what is the distance between the x's? Now x0 and x1 are here, and they are the same axis. Okay, it's a revolute joint. So the distance between them cannot change, but the angle can change between them. So this is my 0 again. Now, what is the angle between the x's? So now if I go back to the previous figure that I drew, so if you can see, this is the top view. It means I'm looking from here. So when link 1 is rotating, what is happening? This angle is changing. So if you can imagine, if it is like this, x0 and x1 are there pointing outward. So when the link is rotating, your x0 will remain here, but your x1 will go somewhere else. Okay, so when the link is rotating, for example, if the link has come to this configuration now, okay, then this is your x1 now. That is fixed to link 1. So what is happening? The angle is becoming, this is your theta 1 now. Okay, so what we are seeing here is that what is the variable angle is theta 1 here. Okay, so if you should be able to imagine that. If you imagine the top view, it becomes very clear that x1, x0 will remain there, but x1 is going to move out. Let me draw it. So when theta 1 rotates, what will happen? X1 will come this side, or it will go that side on the plane. Okay, this is on this plane. Okay, so depending on clockwise or anti-clockwise. Now let's look at, so this is the first one. Now what about the second one? The second one is axis 1 to axis 2. Now we have to be a little careful, because axis 1 is a revolute axis and axis 2 is a prismatic axis. Okay, now when axis 2 moves, what will happen is this linkage, let me go back here again. Let me just go back to the previous figure here. Yeah, so we have said that axis 2 is this one again. The linkage 2 is this one. Okay, so when this moves, when this one moves, what will happen is the axis 2 is fitted here onto this link, right? So this is my Z2, the origin is there. This is my Z0 and Z1, which is fitted onto this link now. So my Z0 and Z1 are there. Z2 is here on this link. So when this link moves like that, what will happen? The distance between this point and this point will change in this direction. Okay, I hope that is clear. So what will happen is, if this fellow comes, moves like this, okay, the second Z origin has gone here now. This is my Z2, this is my X2. Okay, so the origin distance has come, and that is my distance D. Okay, so when it moves in a prismatic joint, the distance between them will change. So that is what is my distance between them. So now A is the link length, A is the distance between the Z's. Okay, Z1 and Z2, what is the distance between them? There is no distance between them. Okay, there is no distance between the Z axis, because they're intersecting at a point irrespective of where the origin is. So the origin can go this side or this side, but they are still intersecting there, because an axis extends in both directions. So it's 0. What is the angle between the Z axis? Now we have to be careful that Z1 was in this direction, whereas Z2 is in this direction. So we have rotated like this in a clockwise direction by 90 degrees. So this is a minus 90. Okay, how do we define clockwise and anti-clockwise? So in robotics, what we are seeing is X, Y, and Z, Y and Z. Okay, so clockwise is defined as you're standing here and seeing in this direction. Okay, so we are sitting on the Z axis and looking towards the origin. We are looking towards the origin, and this is clockwise, which is taken as minus, and that is anti-clockwise, which is taken as plus. Okay, now please note this, because there are two conventions. One is you sit in the origin and you look outwards, and the other is you sit outside and you look towards the origin. So we are following this convention where you're sitting out of the axis and you're looking towards the origin. So clockwise, anti-clockwise is defined like this. So this was a clockwise rotation by 90 degrees, and so it is minus 90. What about the distance between the axes? Now when the joint 2 moves, axis 2 moves, what will happen? The distance between x1 and x2 will change. Again, going back to the previous figure, okay, what will happen is, here we have seen that your x1 is here and x2 is here. So this distance will change when the joint, when the axis 2 moves. Okay, so this is my distance t2. What is the angle? There is no angle there. It cannot. It's not a revolute joint, so there is no angle. So it's 0. What about 2 and 3? Where is 2? 2 is this. 2 is this axis. Where is 3? 3 is axis on the wrist. Now 3 is a revolute axis. Do we see what is A? A is the distance between the Z axis. Now the Z axis are intersecting, because the axis can be extended on either direction, and it is intersecting. So it is 0. What is the angle between them? It is the same axis, right? It is the same straight line. So it is 0. What is the distance between the x axis? Okay, now there is no distance between the between x2 and where is the x-axis? So what is the distance between them? So there can be a distance between x. Where is x3? X3 is here and x2 is there. Okay, so there can be a distance here, but at the moment I'm saying that there can be a small distance there, but at the moment I'm saying it is 0. Okay, So basically what we are saying is, depending on the position of where this, suppose we have a small link length there, that means the axis, the D is only till here, so that is my D2. Okay, that's my D2, and there is a small length here, which is the distance between here to there, that is L. So I can say this is L, or I can say that is 0. Okay, so let me make that as L. Okay, and what is the angle? It is theta 3. Okay, so what we are saying is that this is the DH parameter table for this linkage, which consists of 3 degrees of freedom, 2 revolute joints, 1 prismatic joint. Okay, and the thing to note here is that the z-axis, z1 and z2 are intersecting, so we have to assign the x to be perpendicular to the plane containing the z's. Okay, I hope that was clear. Now this can be a little confusing. Please look at this carefully. So in the full linkage, if I just go back here, okay, so my z2 is here, okay, and it is moving by a distance. So z2, and let me draw it clearly so it becomes clear what is that distance. Okay, so this is one link, this is the other, sorry. Now my z1 and z0 are there. Okay, now z2 is on, the origin is here, okay, and z3 is here. Okay, now z2 can move by a distance. That means when this linkage is moving like this or like this, the distance between this and this is changing. That distance is changing, that is my D. But there is also a distance here, from here to here, there is a distance, that is my distance L. This is a fixed length, so that's the distance between the x-axis. So this was x2, that is x3, that is L now. Okay, so the distance between the origin of 2 and first frame is my D, which is varying. Now the distance between my z2 and the origin of the second axis and the third axis is my L. That is the one that I have drawn here, is L. So I hope this is clear. The important part here is to understand about the z1 and z2, which are perpendicular axis. Okay, so we have covered 2 cases. They are where they are parallel and where they are perpendicular. Now let's look at another example as we proceed. Okay, so let's look at this example also as we are proceeding. So this is another manipulator. Let's look at it like this. This is a manipulator here. And okay, so let's try to understand first of all when it moves, or how does it move. Okay, so when it is rotating, what are the axes? So this is 3 revolute, 3 degrees of freedom manipulator. Okay, so first thing that we do is what we put our axis, the z-axis. Z-axis is axis of rotation, so this is my axis of rotation, that's my third axis. I hope you can visualize. So when I draw the top view of this, let me draw the top view. The top view is going to be the top view will be like this, and this, sorry, let me just change the view again. So this is, otherwise it's difficult to visualize. So this is one, okay, and the other is going to be in this direction. Okay, so this is my, this is not exactly aligned as third angle, first angle, but you can imagine. So if this, so the axis is here, perpendicular axis. So when it rotates, this full thing rotates this side or this side. So it can go this side or it can go this side. Okay, so this full link can rotate about this axis. So this link can rotate in that side or this side. That's my first axis. Now, where is my second one? So this was the first axis. Where is my second axis? The second axis is this axis. Okay, so this is my second axis. This is 0 and 1. This is Z2. This is my axis. Okay, now if you see the side view, what can happen is this can go up or this can go down. Okay, that's my second axis. Where is the third axis? The third axis is here, so it can rotate like that. That's my Z3. Okay, so we have ended up with 3 axes: z1, z2, z3. z0 is the base. Okay, it's the base axis which is always there. Now let us write our dh parameter table now. Okay, so there are 3 revolute axes. We have fixed our z axis. We have to fix our x axis now. Now here we see that z0, z1 are the same line. Now z2 and z1 are again intersecting. So what is going to happen is x is going to be perpendicular to the plane containing the z's. Which is the plane containing the z's? This is the plane. Okay, so it is perpendicular to that. So x0, x1, sorry, I'll just write the numbers. x0 and 1 and 2 are the same axis, and x3 is here. Okay, so now let's write a alpha d theta. Okay, this is the distance between the z's. This is angle between z's. This is distance between x's. This is angle between x's. That's how we remember. So this is distance. This is the relation between 0 frame and first frame. This is second frame, third frame, 2 to 3. Okay, so now let's start off with the first axis. The 0 axis and the first axis, they are the same axis. You can see that. So what is the distance between z's? The distance between the z is the same axis, so it is 0. What is the angle? It is 0. There's no angle between them. What is the distance? It is the same line, so there's no distance between x's. Okay, you can see the x's are the same line. Now when x1 rotates, what will happen is the x1 will come, let me use some other color. So x1 will come this side, or it will go that side on this plane. Which plane? On this plane. So this is the plane. Okay, so x will go this side, or x1 will go that side, or x1 will come this side. That means the variable here is theta1 here. That is the angle between x0 and x1. Okay, next we see the relation between the first frame, the second frame, and the first frame. So what is a? A is the distance between the z-axis. Where is the second frame? It is here. Where is the first frame? It is here. They're intersecting at a point, right? So there is no distance between them. Now what about the angle? Now z2 and z1 have 90-degree angle between them. So this is my 90-degree angle. So how did z1 become z2? It rotated clockwise, okay, by 90 degrees about the x-axis. So if it is clockwise rotation, it is minus 90. Okay, so you're sitting here and looking in that direction towards the origin. So it is clockwise. What is the distance between the axes? There is no distance between the axes, right? They are the same axis. And when x2 rotates, what will happen? x2 will come up or down. So if you can imagine now, x1 was sitting on the top plane. Okay, now where is x? When x2 rotates, what is going to happen is x2 is going to come down like this, so it will go there. Okay, on the vertical plane. So what is the angle between them? It is theta2. Okay, so you can imagine that x1 is here and x2 is the same axis, but when it rotates like this, what will happen is x2 will go up or it will come down depending on how it is rotating with respect to x1, and that is my angle theta2. What about the third one? The third axis we see is here, and z2 is here. Now what we see is that what is the distance between them? Let's say there is a distance between them here. Okay, so there is a length between this axis. Let me use some other color. So there is a length between this axis, this one and this one. What is that length? Let's call it L. So there is a link length L there, which is the distance between the z-axis. What is the angle between the z2 and z3? It is 0 again, because they are parallel. The z2 and z3 are parallel lines. So there is no angle between them. What is the distance between the x's? Now see very carefully that I have fixed my z-axis here. The third axis origin is here, and the second axis origin is there. So if I project it this side like this, if you can imagine that, okay, this is on here, it is coming here, and this is here. So there is a distance there. So there is a small distance there, which is, let's call it d. Okay, so what I'm trying to say is that the origin of 2 and origin of 3, origin of axis 2 and origin of axis 3 are not on the same plane. Okay, so there is a slight shift along the x direction, in the z direction, by this much distance here. You can visualize that, and that is my distance d. Okay, and so d is the distance between the x's. So x2 is in this direction, x3 is in this direction, so you can imagine there is some distance here. Okay, so this is my x2, that is x3, so there is a distance here, and that is my distance d. This is d. And when it rotates, what changes? The x3 and x2 angle will change, so this is theta 3. Okay, so this is an example of another manipulator where we have assigned our a alpha d theta and made the ds parameter table. Now, using this ds parameter table, we have to make the homogeneous transformation matrix from one frame to another frame. That is the objective of making the ds parameter table. Once we make this table, I can find the relation, the transformation between the first frame to the 0th frame, second frame to first frame, and third frame to second frame. So in this case, if I want to find t0 to 3, this will be equal to 0 to 1 multiplied by 1 to 2 and 2 to 3. So each of this is a homogeneous transformation matrix which we studied in the previous class. Okay. Now let's do one more example before we stop. So it is very, very important that you understand ds parameters very, very clearly. Okay, there is nothing complicated here, but you just need to pay attention and understand what these parameters are and why there are 4 parameters. Okay, that is essentially to align an axis with another axis. Let's look at another example. In this case, we look at a SCARA manipulator. Okay. A SCARA manipulator has 4 degrees of freedom, and it has 3 revolute joints and 1 prismatic joint. Okay. So I will very quickly draw a SCARA manipulator. So we had explained a SCARA manipulator earlier, that is used for electronic assembly. And this is okay. So this is our SCARA manipulator having 4 degrees of freedom. So the first thing, what are the 4 degrees of freedom? And corresponding to that, we'll put our axis. So this is the revolute axis, okay, like this. So we can say that is my revolute axis here. We shall call this Z0, Z1. Z0 is reference. We put it Z0 and Z1 is put together to avoid one transformation. This is Z2. Okay, let's see origin there. Now the third axis is a prismatic axis. So it is fixed onto this link here, and it is a prismatic axis. So my axis direction is this side. Okay, but it's a prismatic axis. Now the fourth axis is a revolute axis, but it's facing downward. So the axis direction is this side. It's a revolute axis. So these are the 3 axis directions. So this is revolute, revolute. This is prismatic. It can move up and down. This one is revolute again. Okay. Now I have to put my x-axis. So x-axis I put here. Okay. So x0, x1. This is x2. This one is my x3. This is my x4. Okay. So I have put my z-axis and I put my x-axis. Now for simplicity, I have put z0 and z1 at this point. Actually, there are distances. These distances are there. Okay, but I'm just trying to simplify it by saying those distances are not there in a simplified case. Now this is the link length. L1 is the length between the z1 and z2. This is the link length here. Okay. Now the third joint can move up and down by a distance d3, and there is also a link length here. Okay, so the length from let's say from here to here is L3. Okay, this is a fixed length, and this one is my theta 4. Okay, so there are variables here is theta 1, this is theta 2, that is d3, and there are theta 4. Okay, the other parameters are all given. So let's write the ds parameter tables, a, alpha, d, and theta. So this is 0 to 1, this is 1 to 2, this is 2 to 3, and this is 3 to 4. Okay, let us again write down. This is the distance. A is the distance between z's. This is the angle between z's. This is distance between x's, and this is angle between z's, angle between x's. So let's start off with the first one. The first 0 and 1 axis is the same axis. So this is 0, 0, 0. Theta 1 is the variable. They are the same axis. Origin is the same. What about the second one? The second one is between axis 2 and axis 1. What is the distance between the z's? You can see that this is z2, this is z3, and that is z4. Okay, this is z4. So what is the distance between 2 and this is L1? Between z2 and z1. What is the angle? They are parallel, so it is 0. What is the distance between the x's? There is no distance between the x's. They are the same axis. Now What is the variable? It is theta 2. What about the third one now? Now the third one you have to be careful because it's a prismatic joint, right? So what is the distance between the z's? Okay, the distance between z3 and z2 is L2 that you can see here, right? And what is the angle between the z's? They are parallel, so it's 0. But when the third link moves, what will change there? The distance between x3 and x2 will change, right? So x3 will go up or it will come down. So the distance there will change. So this is my variable, which is d3. And there is no angle there, so it is 0. Okay, so please note this part. For a prismatic joint, you have to be careful. Now, there is something interesting here, is that between axis 4 and axis 3, what is the distance between the z-axis? There is no distance between the z-axis, right? Because they are the same axis, but in reverse direction. What is the angle between them? So z3 is that side, and z4 is this side. So it is 180 degrees, whether you're going this side or you're going this side. So is it plus 180 or minus 180? Okay, interesting question. But it doesn't make any difference because we are playing with sine and cos. Okay, so cos 0 and cos 180 is the same. Okay, so what will happen is whether you write plus or you write minus, it doesn't make any difference there in the transformation matrix. This is something we'll come back to a little later. So angle is 180 degrees. I'm writing plus 180 degrees. What is the distance between the x's? So x3 was here and x4 is here. So maybe there is a distance L3 there. Okay, this is the same thing we discussed earlier, that when you have this, when you have the third linkage like this, which is a prismatic joint. Okay, so this is a prismatic joint. Okay, so the linkage, the origin of x3 is there and z3 is there, and z4 is here. z4 and x4 are there. z4 and x4 are there. So now what we can do is, there is the variable distance d, but there is a distance between here and here, that is my L, which is a fixed distance. So my variable here is theta 3. So this is the DH parameter table for the SCARA manipulator, and with this we will stop today. And please do understand very carefully how DH parameters are assigned and how do we make our DH parameter table. In the next class we'll move forward and look at a few more examples, and then look at how do you make the DH parameter table for larger manipulators or industrial manipulators. So today we'll stop here. Thank you.